Okay, I think we can get started. Welcome to the Silicon Valley chapter of IEEE Computer Society event. I am the chapter chair, Vishnu Pendyala. Ours is the largest chapter in the Silicon Valley section of IEEE with over 4,000 subscribers in our mailing list and a strong following of over 12,400 on Twitter alone. We are uniquely positioned by the virtue of our location and available expertise, and thanks to the virtual mode these days, we are able to get distinguished speakers like Dr. Yung-Hsiang Lu. He'll be talking on worldwide camera networks. It sounded very interesting when I first looked at it, and so the idea is more than 80% consumer internet traffic is for videos, and most of them are recorded videos. Meanwhile, many organizations such as national parks, vacation resorts, Department of Transportation provide real-time visual data, both images and videos. These videos allow internet users to observe events remotely. This talk explains how to discover real-time visual data on the internet. The discovery process uses a crawler to reach many web pages. The information on these web pages are analyzed to identify candidates of real-time data. The data is downloaded multiple times over an extended time period. Changes are detected to determine whether it is likely to provide real-time data. The data can be used during an emergency. For example, viewers may check whether a street is flooded and cannot pass. It is also possible using the data to observe long-term trends, such as how people react to movement restrictions during the COVID pandemic. Today's speaker is Dr. Yung-Hsiang Lu. He is a professor at the Elmore Family School of Electrical and Computer Engineering at Purdue University. He is a fellow of the IEEE since 2021, ACM Distinguished Scientist 2013, and ACM Distinguished Speaker also in 2013. In 2015 and lasting till 2019, he was co-founder and advisor of a technology startup that received SBIR-1 and SBIR-2. SBIR stands for Small Business Innovation Research. In 2020 to 2022, he was the director of the John Martinson Engineering Entrepreneurial Center at Purdue University. His research topics include efficient computer vision for embedded systems, cloud and mobile computing, and he leads a research project analyzing real-time video streams from thousands of network cameras. He is the lead organizer of the IEEE Low-Power Computer Vision Challenge since 2015. He has published 2 books. One is Intermediate C Programming, and the second one is Low-Power Computer Vision, Improve the Efficiency of Artificial Intelligence. So before I turn over the control to Professor Yung-Hsiang Lu, just wanted to mention that please, the speaker wants the session to be interactive, so please feel free to post your questions on the chat window or unmute yourselves. And mute, after asking the question, please remember to mute as well, so that there's no background noise. The speaker would like to keep it interactive, so please feel free. And those on YouTube can post your questions on chat window in the live chat, and I will relay them to the speaker. Links to the video and the slides will be posted on our website in about a week. So with that, a little bit of logistics, I now turn over the control to Professor Yung-Hsiang Lu. Please take it over.
Thank you. Thank you. It is a great honor to have this opportunity speaking here. Let me move. Okay, I think you can see my slides, right?
Yes, we are able to see your slides.
All right. It's a great honor to share my experience about worldwide camera networks. I'm from Purdue University. My name is Yung-Hsiang Lu. I hope this can be very interactive, so please feel free to interrupt with your suggestions, opinions, questions. And better, if you disagree, then that will be even better. We have a good discussion. Today, I will share with you some of my research, in particular in three different topics: how to observe human mobility internationally during COVID. The second part of the speech will explain how we discover network cameras. Then I have a few slides explaining how to think about resource management for analyzing video streams from network cameras. Then the last part of today's speech will be some lessons I learned over the last few years about research and commercialization. First, I want to ask you, does anybody know where this place is?
Yeah, if I remember correctly, it's in Beijing, the downtown Beijing area.
Actually, no. Anyone else? This is in New York City.
Oh, okay.
How about this place? That's also New York City. It's a different angle.
Okay.
Can anybody guess where this is?
St. Patrick's Day.
That's a good start. Dublin, Ireland. So why do I show this? Because as we know, in 2020, COVID occurred and the whole world stopped. You can see from the left side, it was a picture taken in 2019 in New York. And the picture on the right side was 2020 in April. You can see a strong contrast between these two images. We often say a picture is worth 1,000 words. And in this example, the picture really tells us a lot how the world changed when COVID hit about 3 years ago. I have a few more pictures. Again, on the left side is 2019 in New York. On the right side is 2020, April in New York. On the left side was the St. Patrick's Day in 2019. On the right side, it's also St. Patrick's Day, but there are very few people here. Before I go on, I want to express my gratitude to all the people they have helped us in the last 3 years, including utility, network, public safety, emergency, and so on. Today's speech was more or less covered by this research paper published last month, Observe Human Mobility Internationally During COVID-19. This work started in March 2020, and it took us 3 years to get this paper published. But let me review the timeline of this entire project. This project actually started in 2012 when we had almost a very interesting and unusual idea. I will explain that. Then we start building prototype in 2013 and 2014. Then in 2015, we started thinking, is there any commercial value of that? So I participated in a program called the Innovation Core from the National Science Foundation. And we received some more research grant. Then my students obtained the first SBIR grant. SBIR means Small Business Innovation Research. This is a grant given to a startup company. And the company received a second SBIR in 2017. This project received one of the Best Paper Awards in the IEEE Homeland Security Symposium 2018. Then we published a paper called See the World from Network Camera in Computer in 2019. There's another group of students also started a company, obtained SBIR at the end of 2019. Then in 2020, COVID hit, And this research really started when Purdue campus was closed, and some students asked me in a video called, "What can we do for humanity?" And I hope after 3 years, we are able to answer that question from a computer researcher's viewpoint. I'm not a medical doctor, so that was an interesting challenge for all of us. Over the years, we have published some papers. We have also received several patents. This is one of a representative paper. And last month, as I mentioned, we have that paper, Observed Mobility. So the next about 15 minutes, I will share with you our journey over the last 11 years. As I mentioned, in 2020, many universities, including Purdue, closed campus. So that was a Purdue's announcement on March 10, 2020. It says, faculty, staff should move their courses online. I'm sure all of you still remember those few days, how the world has changed. How did this project start? It actually started in 2012 by a joke by a student. A student asked me, "Dr. Lu, I want to see the world, but I don't want to spend money for airplane tickets. Can I see the world without going anywhere? Can I see the world at home?" So we started asking that question. Can we see the world at home? Obviously, we can't download pictures people posted online, but that's a bit boring. We want to see real-time data. We want to see what's happening right now in different parts of the world. The first test we had was to look at the 2014 Thanksgiving parade in New York City. On the left side of this slide, you can see the parade route. And we discovered along the parade route, there are many traffic cameras. The data is publicly available. You can simply do a web search, New York traffic camera, and you can get a map like this. If you click a particular camera, you can see what is happening in New York right at that moment. So we use that information and we build a very simple system to retrieve the data automatically from the network cameras. This is the Thanksgiving parade in New York City. We were able to watch the parade when we were in West Lafayette, Indiana, Purdue campus. We did not go to New York. In fact, we can say by watching the parade this way, we can see even more than what people in New York can see, because we can see the parade from many different angles. That was the initial success of our project. At this moment, I want to stop and see whether anybody has any questions so far. Okay, so I'm going to continue. And again, please feel free to interrupt if you have any questions or comments. Another example was in 2017, Houston had one of the worst flooding. And we again went to Houston and look at their traffic cameras. The data is also publicly available. And we were able to see the situation in Houston without going to Houston. As you can see, a lot of the streets are underwater. Let me get into more details about what we can discover in these pictures. This is one of the examples. As you can see on the picture, it actually has the date and the time information. That's very useful because we can reference the information on a particular day at a particular time. Also, each camera has an ID, so we can match the images taken by the same camera across different time. It's very important to have a location so we can pinpoint the location of the camera. Our project has discovered more than 100,000 cameras. And that's one of the reasons I started getting into computer vision, because we find out that analyzing this amount of data requires huge amount of effort. If we have a person looking at one camera and spend 5 seconds to identify what's in the camera, what's in the image, whether they are people or they are cars or some other objects. Suppose a person spends 5 seconds per camera, then for 120,000 cameras, that means we need to spend 7 days without sleep. That's the reason I started getting into research of computer vision. In the next few slides, I'm going to talk about how to discover the network cameras and how we can use the data. The information is primarily coming from the following 3 research papers. One is published in ACM Transactions on Internet Technology 2022. One is a paper I already mentioned in Computer 2023. And another paper, the third paper, was published in IEEE Transactions on Cloud Computing 2021. First, let me explain what network cameras are. In this context, the meaning of a network camera is a camera that is connected to the internet, and it provides near real-time data. What do I mean by that? Means the data is updated frequently. The data may not update every second. It may update every minute or maybe even every few minutes. Some of the cameras may provide high frame rate video. We have seen quite a few cameras that can provide more than 20 frames per second. We have also seen some cameras that provide only 1 frame of every few minutes. These cameras can be also divided into 2 categories. The first category will be the cameras that have individual internet protocol addresses, IP addresses. The second type of cameras will have multiple cameras on the same website. If you have purchased a network camera, then you will see something like this. When you configure your camera, it may ask you for your IP address, your network information, and so on. Some newer cameras will have an app. When you turn on the camera, assuming the app on your mobile phone is connected to the internet, then when you set up your camera, your app will have a QR code. Then all the information about your network is available in the QR code. So you put the camera in front, you put the QR code in front of the camera can be set up. Each camera has a unique IP address. That's one type of network camera. Another type of network camera will have multiple cameras on a single website. So that's the picture at the bottom of this page shows. We look at the website, we analyze HTTP structure, and then we crawl the web. I will explain the concept in a moment. The web crawler used is called Scrapy, but there are many different web crawlers. Then we retrieve the links that connect to video data. The next step is we want to exclude static data. If it's a static image or a repeated video, a recorded video, then we don't want to keep that. We want real-time data. And we have a module that will verify it's a network camera, then we put that information into a camera database. Any questions or comments so far? Okay, I'll go on. So the first thing we did was we want to identify the network cameras with individual IP addresses. So what we did is we scan IP addresses. If it's a valid IP address, we'll go on to the next step. If it's an invalid IP address, we'll generate another IP address. How do we know it's a valid IP address? We do ping using network, so we see whether there's network response. For different brands and different models, they have a specific protocols to query the network cameras. So what it means is we will send out particular protocol to query the camera. And if we receive valid answer, then we consider that's a valid network camera, and we keep that IP address. If the answer is not valid, then we will consider that not a network camera. So we will skip that IP address and go to the next IP address. How do we scan the network IP addresses? Each university actually has a range of IP addresses. These are just some examples. If you go to the Purdue website, that is the IP address 128.210.7.200. Each university has a range, and the information can be looked up online. Before we scan the IP addresses, I communicated with Purdue's network security office. I said, I'm doing a research. I'm going to scan IP addresses. Please advise whether that's legal and whether that's technically acceptable, and so on. Purdue's network security office came back to me and said, first, it's legal, we can do it, but they want to see our source code to make sure we don't do anything crazy or stupid. It's a very simple source code. We just go to different IP addresses, send those queries I mentioned earlier, and see the result. The code is pretty short. They look at our code and say, okay, looks like you are not doing anything crazy. You can go ahead. But we do know that the network security offices of these universities will probably notice that we are scanning their IP addresses. So we did a few things to reduce the impact. We don't want them to think we are launching a denial of service attack. So if you scan IP addresses very quickly, it's possible they will consider you are explore the network vulnerability. We don't want that. We don't want them to consider we are doing that. So what we did is, first, we use a very low data rate. We only visit one IP address every few seconds instead of doing that as fast as we can. So that slowed down our process pretty much. Second, we also have a very low success rate, meaning we discover about one valid camera for more than 1,000 IP addresses we scan. So the success rate very low. And also we consider only a few no brands in the query protocols. Many network cameras do not. We also discover many network cameras do not have individual IP addresses. So I will talk to the next part of the discovery process. A challenge is we cannot find the camera's locations very easily. And as I mentioned earlier, one big challenge is some universities will consider that we are exploring their network vulnerability. And indeed, a few weeks after we launched our study, we received a notification from Purdue Network Office informing us to stop this camera discovery because ACM University informed Purdue Security Office and say, we noticed a program from Purdue is scanning our IP addresses. Please stop. So we stopped. So that's the first part of our camera discovery. We discovered around 1,000 cameras by doing this. Any questions so far?
Yeah, I had a question.
Yes, please.
So how do you know? So the query that you run against the cameras is like a finger command, or?
I'm sorry, is what?
In the olden days, we used to do finger to an IP address, and it would output some information. So is that something similar, or?
So basically, if you look at a particular brand, they have many brands, they publish their protocols. So if you send a query to a particular port in a particular format, then you will respond to your query by a particular message. Usually it's some kind of okay, and usually send an image back to you if you follow their protocol.
And the brands announce these protocols? It's public?
Yes, many brands announce their protocols, yes.
Okay, just curious, how many cameras have been discovered so far?
Using this method, we discover, I would say about 1,000.
Oh, just 1,000.
Yes.
So you had to stop the program, and could you continue later, or?
So Purdue security told us to stop. They said they don't want us to, they don't want other university to give us trouble. They receive a notification from another university. Their security office noticed we are scanning their network, and
Oh.
so they want us to stop.
Oh, okay.
Also, the success rate is very, very low. It's not very efficient anyway, so we stopped. Does that answer your question?
Yes, thank you.
Okay. So now let me move to the next part of how to discover cameras. We want to find another way to discover cameras, and we find one way is there are many cameras on the network, web pages. For example, if you go to New York City, you can actually find the cameras deployed by New York City, by some universities, or by some other organizations, for example, TV stations and so on. So next step is we want to find these cameras. What did we do? We start using web crawler. What does web crawler do? You will give a web crawler some websites called seeds. For example, we can give www.purdue.edu as a seed. Then the web crawler will simply go through the website and follow the links. So each of them is a link. But if you click, that will go to another website. So that is a link. So there are many links here. The crawler will analyze the website and follow the links and go to another website and go to another website. So you just keep going to more and more websites. After we go to a particular website, then we can see things like this. For example, again, I use Purdue as an example. Then these are the camera from some research labs. This is the camera from looking at Purdue campus. So the next page, I will go to Illinois and see, okay, this is a camera in Illinois website, University of Illinois. Right now, it's about the 8:30 there, so looks like that's probably true. It's getting dark. And the next one is Iowa. So it's getting, I guess, evening. So you see the shadow is pretty low. So that looks, probably that's live. It says live here, but sometimes it says live. It's not live, but in this case, it seems to be live because we look at the location of the sun. The next one can be more interesting. It's from Japan. Somehow this does not auto start, so I'm going to try to start that here. Right now in Japan, it should be 10:30 a.m. Again, you look at the shadow. Looks like it's pretty bright during the day. This is a famous traffic intersection in Japan. So these are some examples that we can find those. Yes. So we can find a lot of websites. They have a real-time data, and the challenge is how can we grab the data automatically, because we want to go to a large scale. So this is what we did. We give some seed website, for example, different universities. Why do we use universities? Because universities websites are usually more open. They allow you to crawl. Company websites usually will have something called robot. The robot tells you, please do not crawl our website. They don't want you to discover their information. So that's why we usually start with university website. Then we send an HTTP request. After we send request, we will get a page. Then depends on the structure of the page, we may or may not need to render. You probably know most web pages are no longer written by the plain HTML. They usually have a lot of different kind of assets. But either way, we will render the website and extract the links. Then we look at the page and see whether we can find video data. Then we will do the next step is whether that we can see that's a real-time data. I'll explain that in a moment. Then we will follow the links, go to more website, and keep going and see whether that website has been visited. If the website has not been visited, we will do it again. So we basically will go to more and more websites and try to find more and more cameras. This is a typical structure for search engines to work. They will have some C website and go to find as many websites as possible, and then index the different websites. Then when you do a web search, the indexes will help you find the websites. Our purpose is somewhat different because we want to find real-time data. We don't want to just find a web page. We want to find real-time data. Any questions so far?
So basically, you're looking for live videos on the web pages, right? On the
Correct.
website.
We want to see the data that is updated regularly.
Okay. So the way you do it is by scanning the text.
No, we don't scan text. Well, we scan the text to find the video information. Then the next few slides will explain how we actually decide that is the real-time data we want.
Okay, one other question I had from your previous slide is, so you discovered these 1,000 cameras, right? But how would you get access to the content in the camera?
Oh, those cameras, okay, I'm sorry, I didn't mention that. Those cameras, let me try to understand what they are at. Those cameras have no password. Many cameras have no password. For example, if you search, for example, the camera, this camera has no password.
So how do you know that?
So the video stream is publicly available.
Oh, okay.
Does that answer your question? Did I answer your question?
So because there's no password, you're able to access the hard drive or the flash drive?
Okay, sorry. No, we don't have to access the hard drive. So the camera posts the data on the internet.
Yeah, this part I understood, but you discovered 1,000 cameras, right? Using the IP
Yes.
addresses. So those cameras are of any use at all, or they're not useful? In your
they can be useful. For example, they watch a national park, they watch a beach, and so on.
Yeah, but how would you get that video?
Because again, if you go back to this, right? If after we discover a particular brand camera, then again that brand has the protocol already published. So we follow the protocol, and you set the right query, then you get an image or you get a video.
Oh, so you can get a video as well. Okay.
Yes.
Yeah, thanks.
If you set the right protocol.
Okay.
And the depends on the brand. Sometimes is the IP address followed by a question mark and image. Then you get an image. By question mark, by I don't remember. I think video dot motion JPEG. Some particular words after the IP address. Then you get the data.
But isn't that a security breach? I mean, somebody is holding a camera which is on the internet, and the information is all going without their knowledge. I mean, it can go without.
Oh, they first. Okay, so I plan to talk about privacy in a moment. We only look at it. So we actually look at the camera, and we look at the camera. We believe it's looking at public locations. We did discover a few cameras. They should not be publicly available. It looks like somebody's house, and we just exclude it. We did check that.
So that is your call, basically. The camera doesn't have a control. It's
oh, they have control. They either intentionally or unintentionally make the data publicly available on the internet.
Oh, okay. Yeah.
We do not use any. We do not guess password or anything like that. We only access data that is publicly available. Everybody on the internet can see.
Okay.
Whether that's intentional, that's not our decision. But we have found a few, not many, maybe a few. We look at it, now looks like somebody's house. We'll say no, we don't want to see it. So we did not keep the IP address.
Okay.
And since you bring it up, this research has been reviewed by Purdue Institutional Review Board, and we follow the protocol for the privacy protection.
Okay.
Any other questions?
Now, this is quite interesting, actually.
So once we move into this process, then we realize there are many different kind of HTML structures. Here are a few examples. And the different HTML structures means we have to analyze them and figure out how to retrieve data. For example, on this picture, there is a map that's not Google Map format. If you have a human move your mouse to a particular place and click, you can get the image or video. This is another example. And some cases, there are images on the web page already. So there are many different structures. We need to write the computer programs to analyze them and get the data. That's the first challenge. Our method has to understand the different HTML structures. So that's the first challenge. The second challenge is some of them require JavaScript enabled. If you enable JavaScript, you can see the map. If you do not enable JavaScript, you cannot see the map. And many of them, most of these websites are designed for human interaction. Really expect human to click or move or answer some questions, then data will show up. They are not designed for computers to analyze automatically. And in particular, so many different formats. So what we did is we actually went to that website and take that information into a web page render, and try to analyze them as automatic as possible. Then the next challenge is to find out the locations. In some sources, we can find locations from the source, assuming the owner gives the correct location. For example, if you go to a particular camera, it may tell you it's at the intersection of a 23rd Street and the East Madison. I think that's from Seattle. And this on the upper left, I think that's from New York. On the right side, you can actually see that's actually from London. You can see the transportation of London. And they also tells you where it is. We usually rely on this information, but that information may or may not be correct because we don't have a very good way to find out whether that information is correct. What we have done is somehow approximation. Based on their location, we will try to see whether we can match, for example, time zone or weather. Imagine this was I did a few days ago when I was preparing today's speech. It was sunny at that time, 10:15 a.m. and I see the sun, I see the shadow. So I think there's very good chance this is maybe near Illinois. It may not be the precise location, but we think it's maybe nearby the location. And we also see, for example, when it gets dark, so that's probably related to a particular time zone and so on. Another thing we did was to match Google Street. This is the example. We find a network camera, and based on the information around that image, it tells us it's on a particular street intersection. Then we went to the Google Street and find, okay, looks like these two large displays and that how seem to match. So we can see that this location is probably correct. So that's the best we can do in terms of finding locations. So any questions? Yes.
You're using something like YOLO or something?
Yes, we do use computer vision to detect things. Yes, and I will say more in the next few slides when we talk about the COVID human counting. Yes.
But then how are you going to search the Google Streets? I mean, the search space is huge, right?
Yes. So what we did, we didn't do for the entire set. We didn't do for everything we discovered. We kind of sample a few. And then based on location of the camera that tells us, so go back to this slide, right? It tells the location, or it tells the location different ways. Then we go to Google Street View and find the location, and we find that looks the location from information like this seems to be correct.
Okay.
Any other questions? Okay. So let me answer your question about how we distinguish the real-time data versus non-real-time data. First, we exclude all the information such as we are pretty certain they are not even data from cameras. We do some pattern analysis, find usually icons like that. They have a very few colors. They have a strong contrast, as you can see. So that's one way to exclude those things. Another way is we retrieve the data multiple times across at different. Then we expect most of the data we receive are outdoor. So if you see in this case during daytime and at night, we see the difference. And we do that for multiple days. So we see there's a pattern, sunrise, sunset. That's one way to discover this is very likely to be real-time data. But we have a false positive. In this case, it's some kind of animated video that shows the Earth, the sun, which part of Earth is lighted by the sun. Our method will consider this as a real-time data because the data changes, but it's actually not. We have a few other methods. For example, we retrieve a video. If it's a video file, then we consider that not as real-time data. If it's a streaming video, then we think that has a better chance to be real-time data. So this is our method. We have several ways to measure them. The threshold, it means how much change we want to consider. If there's no change, means the images do not change, then we will accept everything, but that's not correct. But if we require more than 30% change, then that could be too much change. So going back here, even this is real-time data, but the change can be slow. For example, if you just look at the sky, it doesn't change that much, that fast. So we draw the threshold and the precision recall. Let me first define precision recall. As you can see here, precision means how many good results divided by true positive and false positive. False positive means you think it is good, but it's not good. So that is precision. As we can see here, if we have threshold as 0, then precision is pretty bad because that means we have a lot of false positive, a lot of data. They are not network cameras, but we consider them as network cameras. As our threshold gets higher, then our precision gets better, close to 1. But recall gets dropped. What's recall? Recall means we have the true positive divided by true positive and the false negative. False negative means it is the data we want, but we reject it. We should accept, but we reject. So if the threshold is high, our recall gets lower, means we reject many good data sources, as you can see. So we find the threshold about maybe between 0.1 and 0.2, and that gives us a good balance between these two extremes. In terms of crawl depth, so our crawler will follow the links. If we don't follow any link, our percentage of success is low. As we increase the crawl depth, our success gets more to 2. And then if we go to 3, our success goes lower again. So we crawl to the 4 levels away from the seeds. So any questions?
So it looks like you achieved quite a good precision, right?
Yes.
So, okay, so after you discover the content, you'll be talking about probably in the later slides about how you are going to use the content, right?
Yes. So that's the next slide. Okay, so we discover this, and then we say, what can we do? Well, COVID hit. And then we wanted to do something for humanity, but we are not medical doctors. So in a meeting, in a video call after Purdue campus closed in March 2020, so students went home. Of course, everybody was concerned, but I had a video call with my students, including a lot of undergraduate students in my class. And students said, Dr. Lu, can we do anything for humanity? And I said, I'm not a medical doctor. What can we do? Then after some discussions, we say, can we try to count number of people during COVID? And these are some images we obtained from different parts of the world in France. And I think this is Switzerland. I don't remember. So we just count people, and I'm going to skip this. So we actually find this is a figure published in the computer paper last month. Let me explain how to read this figure. The horizontal axis is the time. The vertical axis on the left side is the number of people, and the right axis is the vehicle. The dot here is called leniency index, means how restrictive the policy is in a particular country. It's actually the reverse of restriction, means if it's more restrictive, then it's a lower number. If it's less restrictive, it's a higher number. And then we superimpose the policy changes at a particular time. As you probably remember, most countries had strict policies in March. And some countries, they relaxed a little bit in the late spring or summer and allowed people to get out. And we can see that the number of people and number of vehicles increase pretty obviously, in particular during summer. And as we go to the winter part of 2020, then some countries such as France restrict their policies again, restrict movement again, and we see a bit drop in their number of people and vehicle we can observe. Again, the examples are like this. We look at public locations, we count number of people across time. So that is how we can use it. Does that answer your question?
Yes. So looks like there are quite a few instances when the people were not following the restrictions, obviously, right?
That's also true. But then we draw this figure in a slightly different way as a scatter plot, showing vehicle and the people, and using different symbols for different time. As you can see, this is the time when there was few restrictions. When April to early May, that was the most restrictive, and there are very few people and very few cars. And then in the green means there are fewer restrictions, so they have a lot more people in the cars. And then in winter, again, there are more restrictions and people are, again, we can see this getting fewer here. So this is a different representation of the data. We do understand there are restrictions of our studies. We don't have a historical data to adjust for seasonal changes. So we just one-time observation across more than a year, about a year, during April 2020 to March 2021. We have only outdoor data and only public locations. We don't have access to private locations and or indoor data. The volume of data is very, very large. So we have to reduce our sampling rate because we have so many cameras we are sampling. A common question we receive is, can you detect masks, whether people wear masks? The answer is no, because we have too few pixels. Going back here, you can see these examples. We can count people, but we don't have enough pixels to detect masks. That also means we cannot recognize faces. One problem we discovered is camera may be disconnected by owners for whatever reason. So sometimes camera disappears and we have to deal with that. Again, related to privacy, this project was approved by Purdue's Institutional Review Board. We count number of people and vehicles. We do not recognize faces or license plates.
So did they recommend any changes or the entire project was accepted as is by the IRB?
They look at our data. We gave a sample data, and we also tell them what we do. We only count, we don't recognize, and they see data like this, so they understand we cannot count, we cannot recognize people. Also, based on the human subject definition and the protocol, if it's a public location and you have no way of knowing their identity, that belongs to a particular category of human subject. You basically observe people in a public location, so that is called an exempt category.
So just curious, why would anyone provide this service of live view of a public place?
Many reasons. What we see is TV stations, a lot of them are TV stations. Oh. So if you go to TV stations, they just put a camera on the top of their building. A lot of hotels, in particular the resort hotels, for example, the ski resort hotels. So there are a lot. If you just search, there are just a lot out there.
Interesting.
Okay. Let me go over, I'm going to skip this so that we can go to some of the interesting part. Is we also consider this, is it technology, is it something for commercialization? We have done some work, we have published papers, we think we have done some interesting work. We also have a few patents. And we can see many places in the world simultaneously. And we can analyze the data very efficiently. We have produced several PhDs with a focus on how to analyze very large amount of data very efficiently. That's the PhD thesis by several of my students. So we got interested in, is there a product? Who are the customers? I joined a program by the National Science Foundation called I-Core, Innovation Core. The purpose of this program is to educate professors and the students whether your research project has commercial values. It's called the customer discovery process. I'm going to skip this called the business model canvas. And this is what I discovered. Published paper is very different from creating product. Creating profitable product is very hard, requires a lot of long-term planning. But university are not particularly good for this purpose. And I explain the following several points here. Because university structures have predictable disruptions. We have a semester system. After a semester, students come and go. Even for graduate students, they graduate, so the technology gets disrupted. And the new students join, so we constantly need to bringing people on board. A lot of homework assignments have this concept, tell students to build things from scratch. So very often students are not trained to build things from existing work. If we give a large piece of software written by people in the past, it's usually very hard for them, both technically and conceptually and maybe psychologically, to contribute because our education system usually encourage people to build things from scratch. Also, because of semester system, many students will think, after semester, I'm gone, why do I care? So documentation is usually not very good and transition can be hard. I also find there's a relatively low correlation between grades and the research ability. Over the last several years, I have advised about 500 undergraduate students. Many of them have very good grades, but they can answer exam questions. They may not be able to do research. I also have seen many students, they don't have very good grades, but they are very excited doing research. They are not very good at taking exams, but they can do research. So it's not very easy to create something that's profitable product out from university structure. I think that's an interesting observation I want to share with you. So to summarize, I hope I have given you some ideas about network cameras. They can provide almost real-time data, I have explained a few steps we have taken on discovering network cameras. One major challenge is to handle the heterogeneity of many different brands and different structures of website. I didn't get into the topics about how to analyze data efficiently. Also, I have discovered research is quite different from commercialization. I know many people here are probably expert in commercialization, so I hope I get a chance to learn things from you. So if you have any comments, questions, or suggestions, this is my email address. Thank you.
Actually, your last couple of slides made me think you could have actually started a company and sold it to Google or something, right? It would have been a great idea.
I have a collaboration with Google. They are my sponsor, but they are more interested on the efficient computer vision or embedded system. At least the people I talk to, they are not interested in network camera.
Yeah. So
one thing go ahead, sorry.
Sorry, go ahead.
One thing I discovered is what we think in university and what people in companies think quite different. We are excited about some interesting technologies, but when people in industry look at, they'll ask, is there customers? Are there customers? It's a different way of thinking.
Yeah, that's right. But they can make ad revenue, right? They can generate
maybe.
Yeah.
So my students got excited and started 3 companies, not directly related to this. They use the technology to solve some other problems. Unfortunately, they did not survive COVID because they are all related to customers. And then when the COVID hits, all the stores were closed, so they did not survive. But I think that's a good experience for everybody involved.
So what are the future directions? Like, do you have any future plans?
Yes, so my core research is how to make computers more efficient, how to analyze large amount of data efficiently. That's my core research. I think this 11 years of journey, a network camera, remember I said earlier, it started from a joke. Students say, can we see the world without paying airplane ticket? I think we have a good journey, and whether this will be continue or not, I still need some time to think.
Okay. Yeah, it's a great story of perseverance and a lot of ingenuity. So I don't see any questions on YouTube. There are a few likes, but no questions.
Okay.
Any questions from the Zoom audience? So I guess not. So anyway, we are, I think, on the top of the hour almost. Yeah. So I wanted to thank you and present you with this. I mean, if it was an in-person event, we could have presented you with a plaque, but because this is where is that? Because it's a remote event, I just wanted to share the certificate with you. So thanks a lot for taking time to give a very insightful and very interesting topic. I mean, you showed the timeline and all that stuff. It was very interesting, very inspiring also. The journey is very inspiring. So once again, thank you for the excellent presentation today, and
Thank you.
We'll be able to bring you in person sometime later.
Sounds great. My honor.
Thank you. Have a
Thank you.
Yeah.
Good day. Bye.
Bye. See you.
Thank you. Have a good day.